Okay, welcome. This lesson is going to cover material from Unit 11-12, and it's going to focus on Box D. We're going to take a look at the product rule here. So the product rule is another one of these rules that we have that allow us to calculate derivatives, one of these algebraic shortcuts that make the process of finding derivatives a lot more simple. So we've already looked at the sum rule and the difference rules, which you can apply when you have two functions. We have a function that is made up of two functions added together or subtracted. The product rule is very similar. So it deals with situations where we have some function, we'll call this function h as a function of x, is made up of two other functions, we'll call them f at x and g at x, which are multiplied together. And the caveats to all of this are that f at x and g at x are functions of x, and that they themselves are differentiable, and so on and so on. So if you want those details, you can take a look in the relevant section in the textbook. But the rule itself is that if we want to find the derivative of h at x, so we want to find h primed at x, we are going to find the derivative of f at x, so we'll have f primed at x. We'll multiply that by g at x, and then to this we will add our original function f at x multiplied by the derivative of g at x. So if it's made up of two functions, we take the derivative of the first, multiply it by the second, and add to it the first function multiplied by the derivative of the second. Okay. And the notation that I will use as I'm going through questions is a little bit more compact. I'll say we have some function f at x, and I'll just draw a line here to show you that this is something different here. So that this f at x isn't the same as that f at x. But I'm going to say f at x is made up of two functions, u and v. And I'll just put in brackets here, u and v are functions. I should say functions of x. Okay. Then our product rule becomes that f primed at x is going to be the derivative of the first, u primed times v, plus u v primed, or the first one times the derivative of the second. Okay. So let's take a look at an example of applying this rule here. So we've got a function y equals 3x to the power of 5 times 6x squared plus 8x, and we want to find the derivative of it. And what we're going to use is, well, we're going to use our product rule, because we've got, this divides nicely into two functions. One function right here, the 3x to the power of 5, is going to be our u function, and all of this stuff in brackets over here is going to be our v function, and both of these are functions of x. And both u and v are polynomial functions of the sort that we've been working with all along here. So let's apply our product rule here. And we'll write it out in detail this time. So we've got y primed is going to be, just like we have up above, u primed times v plus u times v primed. So we just work out the derivatives of these individual little functions here. So the derivative of u primed, is going to be, well, we bring down the 5 to get 15x to the power of 4. And then we multiply it by v here. V is just 6x squared plus 8x. To that term, we are going to add, well, we keep u the same, so 3x to the power of 5. And we're going to multiply that by the derivative of v, or v primed. So let's see. The derivative of v is going to be, bring down the 2, so we get 12x, and 8x term just becomes 8. So there's our derivative we got by applying that product rule. And from here, even though it doesn't say so in the question, we should simplify this. So I'll just write that in. Find the derivative and simplify. So how do we want to simplify this? Well, we've got a number of brackets here that we need to expand. So we're going to do 15x to the power 4 multiplied by everything in that first bracket there. is going to get us 90x to the power of 6 plus 120 x to the power of 5. And over here, we're going to have 36 x to the power of 6 plus 24 x to the power of 5. And then we just want to collect our like terms. So we'll have 126 x to the power of 6 plus 144 x to the power of 5. Okay? And that would be our derivative. Okay. Okay. So let's just take a look at another example here of how you would work this out. Another example of using the product rule. Worded slightly differently here, but find the slope of the tangent to f at x equals 3x squared plus 2 times 2x cubed minus 1 at the point 1, 5. So we're not told here to take the derivative, but anytime we see those words, slope of the tangent, by now we know to think, hey, I want to take the derivative of my function. So I'm going to find the derivative f prime at x. And again, I've got two things that are multiplied by each other, so I want to divide this into two smaller or two simpler functions of x. So this first bracket here is going to be my u, and the second bracket is going to be my v function. So when I do my derivative, I want u primed v, and then I want u and v primed. Are the four things that I want here. Okay, so what's u primed going to be here? Nick. Let's bring this down. We get 6x. V, I can just copy over here. It's going to be 2x cubed minus 1. And then I want to add, well, let's keep u the same. 3x squared plus 2. And I want to multiply it by v primed. So what is v primed here? Let's see. We bring down the 3, and we get 6x. Now, where would you go from here? You could expand and you could simplify. Okay, that's what we did in the last one. Sometimes, though, that's not the best thing to do. Okay, here they give us a specific value of x. Okay, now let me say, if you do expand and simplify and then sub in your value of x, you'll get the same answer. Okay, in this case, I think it's going to be easier though if we sub in our x value and then simplify it. Okay, and you'll see why in just a second. So we know we want to evaluate this at x equals 1, so let's just start evaluating here. Because this kind of substitution I can do in my head. If I put a 1 in there, I'm going to have 6. 2 times 1 is just going to be 2 minus 1. I sub in 1 there, the x squared is just 1 again, so I get 3 plus 2, and then I get 6 at the end. Okay. So in this case, subbing in the x equals 1 at the beginning, I don't have to worry about all my exponent rules and collecting my like terms. So I can start simplifying, keep simplifying here. I get 1 in there. I get 5 times 6. So I'm going to have 36 here. Okay. So some cases, it's easier to do the question if you sub in that value for x that you have as soon as you possibly can. Just remember, you can't sub it in until after you've taken the derivative. Some people decide they're going to sub it into the original function, then they take the derivative and they get 0 and they don't know what happened. Okay, so take the derivative first and then do the subbing in. All right, slightly more complicated question. Here we've got a function, x squared plus 2x plus 1 squared. We want to determine the maximum and minimum values. So this is the kind of question that we worked on in class on Monday when we did the first derivative test. Okay. But to do this one, we're going to have to use the product rule. So for determining our maximum and minimum values, let's just think about what we want to do here. What are the order of steps that we're going to follow? Yeah. First, we're going to find the derivative. So we're going to find, in this case, y primed. What are we going to do with it once we've found it? Yeah, and what is that? Oh, so take y primed, set it equal to 0, and then what are we going to do after we've set it equal to 0? We're going to, solve for the critical numbers. And I'll just say crit numbers. Okay, so those critical numbers are those points where the derivative is equal to 0. And what was the point in finding those critical numbers? Yeah, they represented possible locations where our maximum or our minimum could occur, and how do we figure out if they are actually maxima, minima, or some weird thing that we don't know about? Yeah, we're going to do that interval chart. So we'll say chart to check the sign, comma, check sign of our derivative. Oh, and I should say y primed rather than f primed at x. Keep my notation consistent. So we want to check the sign of our derivative in all of these intervals, and that's going to let us know whether we have maxima or minima. So let's start in on step 1 here and find our derivative. Before I can find my derivative, I'm going to have to write this as a product of two terms. Next unit, we'll look at the rule that you can use to evaluate this in one step, which is called the chain rule. But because we don't know that yet, we're going to have to use our product rule. So now we're going to take our derivative. So we've got u and v, and of course we want u primed v, and then we want uv primed. So I'll just, if I have to do this on 2 lines, v primed. And I'll slide the v over a little bit here. Okay, so let's take the derivative of u. That is just going to be 2x plus 2. And we're going to multiply it by v, which is our x squared plus 2x plus 1. To this, we are going to add our original function u, x squared plus 2x plus 1. And that is going to get multiplied by v primed, which is 2x plus 2. Okay. Now we're going to want to set this equal to 0 and start solving here. So I'll just set it equal to 0. How can I start simplifying what I have on the right-hand side here? Even before I expand. I'm going to have 2 of these, so I can do it as 2 times 2x plus 2 times x squared plus 2x plus 1. Okay. Now, I could expand this out, but if I'm solving for values of x, I don't want it in expanded form. I want it in factored form. So let's see if we can factor this thing. What's left to factor here? Well, I'm going to factor, I can factor a 2 out of this expression right here. So I'll have 2 times 2x plus 1. And what about that second term in brackets there? Can I factor that? It's not in his head. How does it factor to, Richard? So now, I got something that I can simplify a lot here. This becomes 4x plus 1 cubed. So I'm still looking for these critical numbers, but I'm only going to have one critical number, which is going to be where this is equal to 0. So x equals -1 is my critical number. Now, so let's set up our interval chart. I kind of chose this example because the interval chart ends up being really simple, because we only have two intervals, -infinity to -1, -1 to +infinity, and we only have two terms that we have to check the sign for, 4 and x plus 1 cubed. And remember, the whole reason for setting up this chart is we want to know what the sign is of our first derivative here. So I'll do the first row here because no matter what happens, 4 is always positive. What about x plus 1 cubed? How is its sign going to change as we go from -infinity to +infinity? I guess that's the only question we have to answer here. And remember, we can always think about subbing in a test value between, if we're looking at this first column here, some test value between -infinity and -1, so -3, -100, -1,000,000, anything like that. So it's going to be negative, and then we cube it, it's still negative, exactly. So this is going to be negative. And in our other interval, we can sub in something like 3, 10, 100, 1,000,000. We add 1, it's still going to be positive. We cube it, it's still going to be positive. So this thing goes, so our derivative changes sign from negative to positive. So what does this tell us? Well, remember, if our derivative is negative, the slope of the tangent is negative, so that's coming down like this. If our derivative is positive, the slope of the tangent is positive, so that's something going up like this. So what kind of a point do we have at x equals -1? If things are changing from negative slope to positive slope, we must have a local minimum, yeah. So we have a local minimum at x equals -1. Okay? And we can go back and we can evaluate our y value. So y equals, we've got to go way back up to the original function, and we sub in x equals -1, and we do that, and we get 0, actually. So our local minimum is y equals 0 at x equals -1.